Welcome to the deep dive. This is where we cut through the complexity, take dense technical stuff, and make it immediately useful. Actionable intelligence, that's the goal. Today, we're really getting into the weeds of modern analytics engines. We're talking about the core techniques behind, large-scale business forecasting and resource optimization. We've been digging into some pretty detailed technical material, source documents for advanced systems, and looking at these forces you to think like the engineers, right? It reveals the precise technical language, the logical structures that often get, glossed over in high-level summaries. This is how we find out how the systems actually think.
Exactly. And our mission for you, the listener, is pretty straightforward. By the end of this, you'll have a clear, functional grip on these technical components. Think of them as the levers you pull when designing data-driven decisions. And knowing this helps you spot the weaknesses, the opportunities, in any analytical plan someone shows you. Our source material actually gives us a really good roadmap. It outlines 5 major areas: data viz, pipeline modeling, hierarchical forecasting, post-forecasting stuff, and optimization. We'll be focusing today on let's say, the heavy hitters, how forecasting is structured, and the logic behind making decisions when resources are limited.
Okay, let's unpack this. Starting with precision in forecasting and modeling. Before you can trust a prediction, you need to make sure you're comparing like with like, right? If you've got, say, 1,000 different product lines, several regions, you just can't run one single forecast for everything. You absolutely have to segment the data first.
Precisely. Yeah, imagine just throwing all your regional sales data together. California's seasonal fashion, maybe Texas's steady industrial gear. Put it all in one model. The system just gets confused. The patterns from one will just look like, noise when mixed with everything else. It muddies the water.
Right. So how does the system handle that crucial segmentation automatically?
The structural element you need is the BY variable. Think of it like the ultimate organizer for your data. It splits the input data into multiple separate series based on whatever category you tell it, maybe product type, region, store number, whatever makes sense. The key thing here is that it allows each of those, maybe thousands of resulting series, to be modeled and forecasted independently within the system. If you don't define that BY variable properly, your model's just fighting too much noise. It really compromises the predictive power.
That makes a lot of sense. Okay, so we've got our 1,000 separate forecasts generated independently, but then the next problem kind of explodes: comparison. Let's say Model A predicts sales for $1 billion industrial part. Errors may be $5 million. Model B predicts sales for a $1,000 niche thing. Errors $500. How on earth do you compare the quality of those two models? Standard error metrics, they're kind of useless because the scale is just massively different.
Yeah, that's a classic challenge in forecasting. The solution has to give you a normalized view, something standard. The statistic that advanced systems really prefer is the mean absolute scaled error, or MACE, M-A-S.
MACE, mean absolute scaled error. Okay, it sounds a bit intimidating, like another Greek letter metric we have to learn. What does scaled actually mean here? And why should, say, a stakeholder care about it more than the usual RMSE, root mean square error?
The scaling is the really clever part. MAC is scale independent. It's normalized, and it's because it compares your model's error directly against the error from a naive model, basically a random walk model, where the forecast for the next period is just whatever the last observed value was. Simple baseline. So what that means in practice is if your MAC is, say, 0.8, it tells you your current model is 20% better than just random guessing for that specific data series. And because that calculation is relative to the naive model on that same scale, now you can finally compare Model A, the billion-dollar product, with Model B, the $1,000 one, completely fairly. It standardizes the benchmark. It gives finance teams, for example, a trustworthy, universal way to judge model performance across the whole company.
That is a powerful insight. Okay, moving up the chain a bit, analytically speaking, let's talk organizational structure. Predictions don't happen in a vacuum, do they? If my model forecasts individual store sales, those numbers better add up perfectly to the district total. If they don't, we hit what the source calls the summing up constraint.
Right. And if your individual store forecasts add up to, say, $100 million, but the corporate aggregate model, maybe that one's optimized for bigger trends, says $110 million, your inventory teams, your supply chain folks, they have a crisis on their hands. Where do they put the staff in the distribution center? Which number is real? Which one do they trust?
Exactly. You need the statistical accuracy from those bottom-up models, but you absolutely need organizational consistency too. So what ensures this alignment across all levels?
That required process is called reconciliation. Reconciliation is the mechanism, the set of adjustments that ensures statistical consistency. It adjusts predictions up and down the hierarchy so that all the aggregated levels like total sales and the disaggregated levels like regional or store sales line up correctly. Doesn't matter if the system favors top-down, bottom-up, or some middle-out approach for the adjustments. The final result must reconcile. Otherwise, the whole forecast just loses credibility for actual planning.
Okay, let's shift gears just slightly. Practical data manipulation. This is critical in pipeline modeling. Often, the raw data comes in really granular, maybe daily sales figures. But the business decision, like a quarterly budget or maybe a weekly staffing plan, needs a forecast of the weekly total.
Yes, and this is where we often see a common misunderstanding. If I was calculating the average daily temperature for the week, sure, I'd use the mean, an average. But if I'm calculating total sales for the week, I can't just average the daily sales figures. That doesn't make sense.
Right. So if the goal is specifically to forecast a weekly total, the correct time aggregation method isn't averaging. It's not the median. It has to be summation.
Correct. You absolutely must use summation. Summation aggregates observations based on what you're trying to achieve. We need to sum the counts, sales, units shipped, transactions to get a true total over that defined period. If you accidentally use an average instead, you create this meaningless metric. It doesn't represent the actual resource amount or dollar figure the business needs to plan for. It seems subtle, but it can break the whole pipeline.
Okay, one last point on forecasting before we move to optimization. Even the best automated forecasting pipeline needs room for human insight, right? The market expert who knows something that historical data just doesn't reflect yet. But what happens in a big company when two different analysts apply different manual adjustments? Overrides. And they do it for the predicted sales volume for the same future quarter.
Ah, yes. That creates an override conflict. Analyst A thinks sales should be $10 million based on their insight. Analyst B thinks $11 million, and they both enter their manual adjustment. When that happens, you need a specialized governance tool. It's often called something like a forecast conflict manager. It has to step in, log the difference, manage some kind of review process, and make sure the final accepted value is propagated consistently. It's basically the data governance layer you need when humans get involved.
Okay, here's where it gets really interesting, I think. We're shifting now, moving from predicting what will happen to the much harder job of deciding what we should do, given our limits. This is the world of optimization, dealing with resource constraints, constrained decision-making. Every optimization problem starts by defining the fixed reality, the things we just can't change. Let's say you're managing production at a car plant. You know you have exactly 4,000 hours of machine time next month. That's it. And the raw material cost is fixed at $50 per unit. These values are non-negotiable inputs. How does the model handle these constants properly?
Well, you definitely don't just hard code them into the equations. That makes the model a nightmare to manage or update later. The proper structure uses numerical parameter declarations. These parameters are the constant values that define your playing field, the max machine hours, the fixed budget, the cost per unit. You define them right up front. They become these non-negotiable inputs that get referenced later in your objective function and, critically, in your constraint definitions.
Okay, contrast that with the actual decisions we're trying to make. Maybe we need to choose between 3 different logistics projects, but we only have the budget for one. We need a way to model that simple on-off choice. Yes or no?
That kind of choice is handled very elegantly by a binary restricted decision variable. Simple but powerful. This variable is mathematically restricted to be either 0 or 1. Nothing else. So if you're modeling, say, a capacity planning problem, the variable is 1 if you decide, yes, lease the new facility, and 0 if you decide, no, don't lease it. It's the building block for any kind of complex selection or routing problem.
Okay, now we get to the real power, I think, of linear programming, the science of constrained decision-making. We talked about constraints, machine hours, budgets. There's this amazing, almost magical concept that connects every single one of those constraints back to the actual economics of the solution.
Ah, yes, the Lagrangian multipliers, often just called dual values. This is where optimization stops being just about finding a number and starts providing real strategic insight.
I remember when I first really understood dual values, it felt like the math was literally putting a dollar value on physical space or machine time. What's the core mathematical truth about them?
Well, first, the number of Lagrangian multipliers you have is always exactly equal to the number of constraints in your model, 1 for 1. But the real power is in how you interpret them. The dual value tells you the rate at which your objective function use lives, usually maximizing profit or minimizing cost changes, if you relax or tighten the corresponding constraints limit by just one single unit. So if the dual value on your machine hour constraint is, say, $500, it means getting one extra hour of machine time would yield $500 in additional profit. Assuming, of course, that constraint is currently maxed out or binding, this is the economic insight you need to justify spending more money, maybe on capital expenditure or overtime. If that dual value is high, you know exactly where investing a bit more will give you the biggest bang for your buck.
Okay, wait. If the dual value is that powerful, why do so many companies seem to just ignore it? They focus only on the final production numbers, right?
Well, partly because it does take a bit more expertise to interpret correctly, and technically it only applies to small marginal changes around the current solution. But yes, failing to look at dual values means you're flying blind strategically. You might be producing the optimal output given your current limits, but you don't know the cost of those limits or the potential value you could unlock by removing them. You're missing crucial information.
However, not all problems are nice and neat, like linear ones. When you get into nonlinear programming, NLP, the solution landscape gets much messier. It's often described like a mountain range, right? Lots of peaks and valleys. If you use an iterative solver, it often finds a high point, but maybe not the absolute highest peak on the whole map.
That common situation, that endpoint, is finding a local optimum. It's a feasible solution, and it gives you the best objective value within its immediate neighborhood, like the top of a small hill. But in non-convex NLP problems, where that solution surface is really complex and irregular, the solver can easily get stuck on that small hill. And it might completely miss the true global optimum, the Mount Everest that's maybe far away in the solution space.
So a local optimum is, okay, it's a great solution nearby, but potentially not the best overall solution for the entire business strategy.
Exactly. And that inherent risk is why NLP needs much more robust testing. Sometimes you have to start the solver from many different initial points just to try and map out that complex landscape more completely.
Right. And one final point on optimization. When you're running these complex models, you often have different software approaches available, like active set versus interior point methods. Our source material clarifies what the choice between these, advanced solution methods actually impacts. What difference does it make?
The choice primarily influences the computational speed and the numerical stability of actually finding the solution. It's not about defining the problem itself, the constraints, the objective. Those are fixed by your business reality. Choosing the solver methodology is really a performance issue. Does your big planning run finish in 15 minutes, or does it take 15 hours? That makes it a pretty crucial decision for business efficiency, obviously.
Let's end then on a provocative thought. Something for you to consider about the constraints in real-world modeling. We talked about two very different kinds of boundaries today, didn't we? Reconciliation ensures predictive alignment within the organizational structure. Constraints and dual values manage physical limits and assign economic value to them. Both are essential. They define the necessary boundaries for making practical, actionable plans.
So consider this. You now understand the risk of getting trapped in a local optimum when optimizing, and the risk of an override conflict messing up your forecast. In your experience, which do you think presents the bigger danger to overall strategic goals? Is it a mathematical limit that might prevent finding the absolute best solution? Or is it unchecked human input that undermines the system's consistency? What stands out to you as the biggest factor threatening the integrity of the overall plan? Something to think about.